On July 1st, 2025, a modest telescope stationed in Chile quietly recorded a faint moving point of light. At first, it seemed like just another comet, one of countless icy fragments wandering through our solar system. But within days, astronomers confirmed something extraordinary. This was no ordinary visitor. Its path was hyperbolic, its speed too great to be bound by the sun. It had entered our system from the deep interstellar dark, a traveler older than Earth itself. They named it 3I Atlas. By October the 3rd, it will pass near Mars, sweeping just 29 million kilometers from the red planet. Weeks later, on October the 29th, it will reach Perihelion, its closest approach to the sun, moving at nearly 68 kilometers per second. Unlike familiar comets, Atlas carries an unusual chemistry. Carbon dioxide dominates its coma in ratios rarely seen in local bodies. Its orbit, retrograde and tilted steeply against the planetary plane, guarantees encounters with the densest regions of the solar wind and the chaotic fields of the asteroid belt. For scientists, it is a chance unlike any other. For storytellers, it is a reminder that the universe is alive with wanderers. And for all of us, it is an invitation to look up and imagine what secrets a billion-year journey might carry into our skies. Stay with me as we follow this interstellar messenger. If you enjoy journeys like this one, subscribe and share your thoughts below. Each part of this story unfolds like a cosmic chapter, and together we'll discover whether Atlas survives its crossing or disintegrates into memory. To understand why 3I Atlas has captured so much attention, we need to step back, not just in space, but in time. This comet's story began billions of years ago, long before our sun lit up the solar system. Somewhere in the galaxy, in a stellar nursery far removed from our familiar constellations, a star was born. Around that young star, a disk of gas, dust, and ice condensed. Within that chaotic, spinning cradle, planetesimals and comets formed, some destined to remain loyal companions, others cast out to wander forever. Atlas belongs to the latter group. Gravitational tugs from forming giants, perhaps the rough encounter with a migrating planet, may have flung it outward with enough energy to escape its parent star entirely. Imagine a child's toy marble spun from a table with such force that it never circles back. For billions of years, Atlas drifted between stars, alone, silent, slowly weathered by cosmic rays and micrometeoroids. It is a relic of a system we will likely never see directly, a frozen archive of chemistry written under alien skies. Most comets in our solar system are dominated by water ice. Water, after all, is abundant here, and its behavior under solar heating defines much of what we expect comets to look like. Yet when astronomers trained the James Webb Space Telescope on Atlas, the spectrum told a stranger story. The balance between carbon dioxide and water was inverted. Ratios approached 8 parts C/2 for every 1 part H2O, an arrangement almost unheard of in our catalogue of comets. What does that mean? Chemistry reflects the environment. The abundance of carbon dioxide suggests Atlas was born in a region of its home system where temperatures were low enough to freeze CO2 efficiently. Still, conditions somehow suppressed the locking in of water. Perhaps its parent star emitted radiation that drove water away. Perhaps heavy dust shaded the disk unevenly, leaving CO2 pockets intact. Whatever the reason, this object carries with it the fingerprints of a planetary nursery that operated under rules different from ours. In a sense, every molecule it releases is a postcard from another world. This is what makes interstellar comets so valuable. They are not just icy rocks. They are samples of other solar systems delivered to our doorstep. With Oumuamua in 2017, astronomers tasted mystery. A visitor with no visible coma but a non-gravitational acceleration that defied easy explanation. In 2019, they witnessed a more conventional comet, rich in water and carbon monoxide, behaving as if it had always belonged here. Atlas arrives as the third, and it feels like a blend of both mystery and familiarity. Its chemistry sets it apart, hinting at the diversity of planetary formation across the galaxy. Think of our galaxy as a vast kitchen where every star stirs its own recipe. Some bake water-rich comets like the ones that seeded Earth with oceans. Others create CO-rich fragments. And then there is Atlas, carrying a recipe heavy in carbon dioxide, showing that even the chemistry of ordinary ingredients can diverge widely. When I consider this, I imagine walking through a farmer's market where every vendor sells bread, but each loaf tastes different because the soil, water, and yeast vary by region. Atlas is that unusual loaf, needed in a kitchen far beyond our neighborhood. Its orbit adds another layer of intrigue. Atlas doesn't simply pass through politely along the flow of the planets. Instead, it comes in on a retrograde trajectory, meaning it moves against the grain of our solar system's rotation. The inclination is steep, nearly 175 degrees, like a salmon swimming upstream in a river of planets and asteroids. Retrograde motion guarantees high energy encounters with the solar wind, with dust, and with magnetic fields. Every crossing is more violent than it would be for an object traveling in the same direction as Earth. This, too, is a clue to its past. Retrograde orbits are not forged locally. They are hallmarks of capture, or in this case, of intrusion. It reminds us that Atlas is truly foreign, unshaped by our sun's authority. It answers only to the galaxy. Consider what this means for the comet's surface. For billions of years, it wandered interstellar space exposed to harsh cosmic rays. Protons and heavy ions pierced its outer layers, shattering molecules, welding some into crusts of radiation-darkened material. Just beneath that fragile skin, however, lie ice preserved since the dawn of its home system. Each layer is a record, a frozen diary of ancient stellar weather. When sunlight now strikes Atlas, it burns through those layers, releasing gases that tell scientists exactly what lies within. Some molecules may be ones we know well: carbon monoxide, carbon dioxide, water. Others may surprise us, carrying exotic isotopes or ratios unseen in our system. Each detection helps refine our picture of how different stars seed their comets. In effect, Atlas is a courier, carrying pages from a book written billions of years ago in another library of the cosmos. Here is where the educational lesson deepens. Comets are not only icy relics, they are time capsules. They show us conditions from the earliest days of planet building. In our own system, studying comets like Halley, 67P/Churyumov-Gerasimenko, or ANEOWISE has taught us about water delivery to Earth, about organic molecules that may have seeded life, and about the physics of dust and plasma interactions. But those lessons are parochial. They tell us what happened here. Atlas expands the classroom. It allows us to compare. It is like discovering a fossil from another continent that forces us to rethink evolutionary history. As I narrate this, I find myself struck by the humility it demands. The galaxy is vast, and we know only a sliver. Each interstellar visitor is a teacher, reminding us that our models are provisional, our assumptions temporary. In the case of Atlas, the abundance of CO2 isn't just a curiosity, it is a challenge. Why do some systems favor this volatile, while ours do not? What does that say about the likelihood of Earth-like planets elsewhere? About atmospheres, climates, and perhaps even the chemistry of life? When I first read the data on Atlas's composition, I felt a peculiar mix of awe and unease. Awe, because it confirms how creative nature can be, endlessly varying the recipes of matter. Unease, because it highlights how little we know. If one comet can show us chemistry so different, how many more surprises are waiting? It makes our solar system feel less like the norm and more like just one regional dialect in a galactic conversation. In the quiet of night, when I imagine Atlas hurtling through the dark, I think about how it has never been observed until now. For eons, it was invisible to every eye, every telescope, every story. Only now, by a convergence of timing and technology, do we get to witness it. That realization makes me grateful. Grateful for the instruments that scan the skies. Grateful for the scientists who interpret faint spectra. Grateful, above all, that the universe occasionally hands us a messenger carrying truths we could never invent. And so, with its alien chemistry, its retrograde defiance, and its billion-year history, Atlas plunges toward the asteroid belt. Ahead lies turbulence, dust storms, magnetic entanglements, solar winds that roar like unseen hurricanes. The comet's unusual makeup may influence how it weathers those conditions. Will the CO2-dominated coma create tails that twist differently, respond more dramatically to solar storms? Will its crust crack more easily, fragmenting into shards? Or will its age and endurance prove it tougher than we expect? These questions prepare us for the next chapter. Atlas is not merely drifting, it is about to run a gauntlet. The asteroid belt has tested comets for billions of years. Most pass quietly, some break apart. Atlas will confront not only rocks and dust, but a storm of invisible plasma fields. In the next part, we will journey with it as it enters that hazardous region, exploring what dangers the belt holds and what lessons it might teach us about survival in a crowded, electrified cosmos. The asteroid belt has always occupied a peculiar place in human imagination. To the popular mind, it is often pictured as a crowded gauntlet of tumbling boulders, where any spacecraft must weave and dodge through a storm of rocks. The truth is subtler, and in many ways more dangerous. The belt is mostly space, but the few objects it does contain move at staggering speeds. For a comet on a retrograde course, the danger is not so much frequent collisions as the ferocity of even the rarest encounter. Every particle of dust, every pebble, becomes a bullet accelerated by relative velocities that exceed anything we can reproduce in a laboratory. As Atlas plunges into this region, the first thing to note is geometry. Its orbit cuts across the plane of the ecliptic at a steep backward angle, almost like a swimmer diving headlong into oncoming waves. The majority of asteroids circle the Sun in the same direction as Earth, but Atlas approaches against the traffic, a rogue vehicle on a one-way freeway. That reversal multiplies energy. A single grain of dust, no wider than a human hair, can strike with the impact of a rifle shot. To imagine this, consider standing on a highway where cars are already moving at 70 miles per hour, and then add another car racing directly toward them at the same speed. The relative collision is not just doubled, it grows into something devastating. For astronomers, the belt offers both peril and opportunity. On one hand, the density of particles means Atlas may undergo surface erosion, jets of gas erupting from impact points, and even structural cracking. On the other hand, those very impacts may act as probes. They may break through radiation-darkened crust and expose pristine material that has not seen light since it froze around another star. Each sparkle of dust against its nucleus could become an unplanned experiment, a miniature excavation ordered by the cosmos itself. The belt is not uniform. Some regions are richer in debris, others sparser. The so-called Kirkwood gaps, sculpted by Jupiter's gravity, carve empty channels, while denser families of asteroids cluster around resonances. Atlas does not care for these neat classifications. Its path cuts through whatever regions happen to lie along its retrograde highway. This randomness is part of what excites observers. They will watch not just for collisions, but for how the comet responds differently, depending on whether it crosses a denser or thinner region. In this way, Atlas is less an intruder and more a surveyor, sketching a cross-section of the belt's invisible architecture with its own tail. The plasma environment complicates things further. The belt is bathed in solar wind, that endless stream of charged particles flowing outward from the Sun. Normally, comets develop plasma tails that align with this wind, revealing its currents like streamers in the air. For Atlas, the situation is magnified. Moving against the flow, it will feel the impact of every gust more strongly, its tail whipping and bending with exaggerated drama. Scientists expect to see sudden kinks, disconnections, even entire sections torn free and carried away before reforming. To an earthbound observer, these changes may seem like graceful dances of light. To plasma physicists, they are data points, evidence of magnetic reconnection, shock waves, and turbulence on a scale impossible to study otherwise. I find it striking to think of the comet's tail as a windsock at an airport, silently recording the direction and intensity of the gale. Yet here, the wind is invisible, made of particles and fields that our senses cannot feel. Only by watching the comet's luminous response do we learn the shape of the storm. It is a reminder that much of space weather is hidden from direct perception, yet it governs the reliability of satellites, the stability of power grids, and the accuracy of GPS clocks. What seems remote and exotic has consequences that reach down into the devices we hold in our hands. There is also a psychological drama to this crossing. The asteroid belt is a threshold, a region of myth and story as much as of stone and dust. For centuries, it was thought to be the remnants of a shattered planet. Later, we learned it is the raw material that never coalesced, held apart by Jupiter's gravity. To see an interstellar visitor dive through this zone is to watch one archive of cosmic history pass through another. One is the frozen remnant of a system beyond our sight. The other is the unfinished chapter of our own. They meet in silence, but the implications echo loudly. How many such meetings have occurred unobserved? How many interstellar objects have been erased by collisions we never knew? The educational lesson here is humility in statistics. We often think of probabilities as comforting. The chance of collision with a major asteroid is vanishingly small, so we can relax. But low probability does not mean zero. Over billions of years, even rare events accumulate. An interstellar traveler could easily be shattered, its history lost before any civilization had the tools to witness it. That Atlas has made it this far intact is itself a selection effect. We are seeing it because it survived. Many others did not. In this way, every observation is biased toward the lucky survivors, the ones strong enough or fortunate enough to evade destruction. As Atlas progresses deeper, telescopes on Earth and in space will monitor every twitch of its brightness. A sudden surge may signal an outburst triggered by thermal stress or an unseen collision. A fading could hint at fragmentation, the nucleus splitting into pieces. Instruments sensitive to polarization will measure how sunlight scatters off dust grains, revealing their size and composition. Radio antennas may detect plasma waves as the solar wind slams against its coma. Each instrument adds a layer of understanding, like doctors monitoring a patient with a suite of sensors, each one telling part of the story of health or decline. From a personal perspective, I find myself drawn to the resilience implied in this crossing. Atlas has already endured billions of years alone, traversing environments far harsher than anything in our solar system. Yet the belt is a new ordeal. It is not just emptiness, but structured emptiness, where rocks and dust are spaced out like landmines. The comet has no agency, no awareness of the gauntlet. It simply follows its path, obeying gravity and momentum. And yet, there is a metaphor for us in this blind passage. We too move through invisible hazards in our lives, some statistical, some certain, unaware of which will strike. Like Atlas, survival is partly strength, partly chance, and always fleeting. By the time the comet emerges on the far side of the belt, its story will either be one of endurance or of unraveling. If it survives intact, it will offer its most dramatic display as solar heating intensifies near Perihelion. If it fractures, we may witness the birth of multiple comets, each fragment telling a slightly different version of the same tale. Either way, the crossing is decisive. It sets the stage for what is to come. The belt is both trial and prologue. Looking ahead, the focus will shift from rocks and dust to the comet's own growing expression, the tail. For Atlas, dominated by carbon dioxide, that tail will not just be a luminous streamer of gas and dust. It will be a laboratory of plasma interactions, a visible signature of how alien chemistry dances with the solar wind. In the next chapter, we will follow that transformation. The visitor will cease to be a point of light and become a sprawling structure hundreds of thousands of kilometers long. Its every twist a clue, its every shimmer a message. The comet is about to reveal itself in full. By the time Atlas pushes deeper into the inner regions of the asteroid belt, its identity begins to shift. What once looked like a faint, moving star becomes unmistakably a comet. The coma swells, a hazy atmosphere of gas and dust surrounding the nucleus. From Earth, it appears as a delicate blur, but in reality, that envelope stretches for hundreds of thousands of kilometers, a miniature atmosphere carried along with the comet as it races forward. Out of that coma extends the most dramatic feature of all, the tail. Every comet forms at least one tail, often two. There is the dust tail, made of tiny grains lifted from the surface by escaping gas, and there is the plasma tail, composed of charged particles carried away by the solar wind. To the human eye, these tails appear as luminous streamers in the night sky, sometimes broad and curved, sometimes narrow and straight. For scientists, they are more than decoration. They are diagnostic instruments. Their shape, their brightness, and even their instabilities tell the story of the invisible environment through which the comet travels. In the case of Atlas, carbon dioxide is the dominant driver. Unlike water, which requires the comet to be fairly close to the sun to sublimate, carbon dioxide can vaporize at much lower temperatures. That means Atlas began releasing gas earlier, forming a coma and tail well before its perihelion. The timing matters. It extends the window of observation, giving astronomers months instead of weeks to measure the composition, the flow, and the evolution of this alien material. The CO2 dominance also changes the character of the plasma tail. Carbon dioxide ions, when struck by sunlight, follow spiraling paths along magnetic field lines that differ from those of water-derived ions. The tail may therefore exhibit structures and instabilities that no other comet has shown us. In this way, Atlas is not just another object in the catalogue. It is a controlled experiment set up by nature itself. Watching a comet's tail can feel like watching an artist's brushstroke in slow motion. The brush here is the solar wind, invisible and relentless, dragging particles into filaments and sheets. The ink is the gas of another star system, glowing faintly as photons scatter off it. The canvas is the vastness of interplanetary space, and the result is something that combines elegance with vulnerability. For even as the tail grows, it remains fragile. Coronal mass ejections, great eruptions of plasma from the sun can strike, like gusts of hurricane force, snapping the tail in two, sending entire sections adrift like torn fabric. Hours later, the comet will regrow its streamer, only for the process to repeat when the next storm arrives. Time-lapse images of these tail disconnection events are among the most dramatic in all of astronomy. A straight, luminous line suddenly bends, kinks, and finally detaches, drifting away into space. To the naked eye, these transformations might go unnoticed. But through telescopes, they become clear records of solar weather, a language of shape and brightness that translates electromagnetic turbulence into something we can see. Atlas, with its unusual chemistry, promises to write that language in new dialects. Its tail will not only bend and snap, but may also ripple with patterns scientists have not yet modeled. Dust complicates the picture further. Every dust grain released from the nucleus acquires an electric charge, thanks to ultraviolet sunlight knocking electrons loose. Once charged, those grains no longer follow only gravity and radiation pressure. They dance to the tune of electric and magnetic fields. Their paths twist, sometimes diverging from the gas tail, forming broad fans or delicate striations. Laboratory experiments on dusty plasmas show that such grains can even organize themselves into waves and clusters, like schools of fish swimming in patterns no single individual controls. To imagine this around Atlas is to envision a natural laboratory stretching millions of kilometers, where microscopic dust acts like both participant and probe. What fascinates me is how all this complexity comes from the simplest of beginnings. A frozen block of ice and rock, heated by sunlight, begins to release gas. That gas carries dust. The gas is ionized by photons, turning into plasma. The plasma interacts with magnetic fields, twisting and breaking. Suddenly, what began as a piece of cold matter becomes a glowing, structured, and ever-changing phenomenon visible across millions of miles. To me, it feels like a metaphor for human expression. Pressure builds, heat rises, and out of what seems solid and mute emerges a stream of visible energy, shaped by forces outside our control, yet still uniquely our own. For the scientific community, Atlas's tail offers a chance to validate and refine models of plasma physics. Computer simulations struggle to capture the turbulence of ion tails, where countless charged particles interact through long-range electromagnetic forces. Observing Atlas in real time provides constraints that theory alone cannot supply. In fact, researchers have begun to speak of comets not merely as icy bodies, but as probes of space weather. Where spacecraft give us data at a single point, a comet's tail provides a sprawling, dynamic map. Watching its movements is like stretching out a vast net into the solar wind and seeing which way the currents pull. There is also a lesson here about resilience and fragility. The nucleus of Atlas may survive, hard and ancient, but the tail is forever at the mercy of its environment. It grows, it breaks, it reforms, again and again. From one perspective, this makes it fragile. From another, it makes it enduring. No matter how many times the solar wind shreds it, the comet grows a new tail. In its own way, this cycle is a form of persistence, a reminder that survival is not always about resisting change, but about adapting to it. I find that deeply human. Our lives, too, are shaped by forces beyond our control. We lose jobs, relationships, and health. Each loss feels like a tail ripped away. Yet we regrow, reform, and continue our trajectory. As Atlas accelerates toward the sun, the brightness of its tail will increase, and Earth-based telescopes will strain to capture every detail. Cameras will measure polarization to infer dust sizes. Spectrographs will analyze emission lines to determine the ratios of ions. Amateur astronomers may even join the effort, pointing backyard telescopes skyward, contributing images that professionals will use to track rapid changes. The collaboration itself mirrors the comet's own dynamics, small contributions gathering into a larger, coherent picture. By the end of this stage, Atlas will no longer be just a traveler from beyond. It will be a plasma laboratory in motion, its tail not a passive streamer, but an active record of cosmic conditions. Each kink, each flare of brightness will be a data point, a signpost in the storm. Whether or not the nucleus survives, the tails will have spoken. They will have given us clues about how matter from other stars behaves in the crucible of our sun's influence. The story of Atlas is now turning from the broad sweep of orbit and origin to the finer brushstrokes of behavior. In its chemistry, in its tail, in its response to magnetic storms, it is showing us that the galaxy's diversity is written not just in stars, but in the ices of tiny wanderers. What comes next is context. To fully grasp the significance of Atlas, we must compare it to those who came before, the enigmatic Oumuamua and the more conventional Borisov. Only then can we see how this visitor fits into the growing family portrait of interstellar travelers, and why each one is a new lesson in cosmic possibility. When Atlas burst into awareness, many astronomers felt a wave of déjà vu. We had been here before, twice in fact. Each time an interstellar object crossed our skies, it altered the conversation about what the galaxy might be sending our way. Each time, it left us with more questions than answers, and each time, it reminded us that we live in a galactic neighborhood where traffic is real, even if the intervals between sightings stretch across human lifetimes. The first was 1I/Oumuamua, discovered in October of 2017. It came fast and left even faster, streaking through the inner solar system before most telescopes had even adjusted their gaze. Its very name, given by Hawaiian astronomers, means scout or messenger from afar, and in hindsight the name carried more weight than anyone imagined at the time. Oumuamua challenged expectations from the start. Most comets, when they swing near the sun, sprout a coma and a tail, betraying their composition of volatile ices. Yet Oumuamua showed none. It was dark, elongated and silent, tumbling end over end, like a shard broken off something larger. More curious still was the way it accelerated as it departed the sun. The speed change was subtle but undeniable, not fully explainable by gravity alone. Many theories circulated outgassing too faint to see, a fractal structure with high surface area, or even the possibility that we were looking at something artificial, a sail pushed by sunlight. To this day, no single explanation satisfies all the data. Oumuamua remains an enigma, a silent puzzle piece that doesn't quite fit the picture. The second visitor was 2E Borisov, discovered by an amateur astronomer in Ukraine in 2019. Unlike Oumuamua, Borisov behaved almost exactly as astronomers expected a comet should. It released gas and dust. It sprouted a beautiful tail. Its chemistry, though not identical to comets we know, was within familiar ranges. It was as if Borisov came to reassure us. Interstellar comets can look and act just like the ones born in our own Oort cloud. This familiarity was comforting, but it also raised questions. If Borisov was so normal, why had Oumuamua been so strange? Were both equally representative of interstellar populations, or was one an outlier? And if so, which one? Now comes Atlas, the third in the sequence. Already it shows us a different personality, clearly active like Borisov, but chemically distinct in ways that defy easy comparison. The CO2 dominance stands out like a fingerprint from another star system, unlike the water-rich comets closer to home. It reminds us of Oumuamua's strangeness, though in a different form. Atlas seems to occupy the middle ground, active like Borisov, alien like Oumuamua, a hybrid of familiarity and mystery. For me, the sequence feels like a conversation. Oumuamua asked a question. What if interstellar objects don't look like what we expect? Borisov answered, some do, some don't. Atlas now complicates the dialogue further. What if strangeness itself is the rule, not the exception? If 3 visitors can display such diversity, then perhaps our mental picture of the typical interstellar object is deeply incomplete. Perhaps there is no typical at all. Perhaps the galaxy, like any ecosystem, thrives on variety. Each visitor has also taught us lessons about preparedness. With Oumuamua, we were caught off guard. By the time its interstellar origin was recognized, it was already on its way out. Observations were rushed, incomplete and scattered. We learned that discovery must come earlier if we want to gather enough data. Borisov gave us that chance. Its coma and tail made it easier to detect, and astronomers tracked it for months. We learned that interstellar comets could be studied almost as well as local ones, provided they give us enough warning. With Atlas, we are seeing the value of global coordination. Space telescopes, ground observatories, and even amateur astronomers are working together to watch every stage of its evolution. In this sense, each object has been a rehearsal, teaching us how to respond better when the next messenger arrives. The human reaction to each has been just as revealing as the science. Oumuamua triggered speculation about alien technology. Its elongated shape and unexplained acceleration seemed to invite the imagination. Borisov, by contrast, drew less public drama, perhaps because his behavior seemed so normal. Atlas reopens the door to speculation. Its alien chemistry and dramatic trajectory across the asteroid belt make it tempting to weave stories of hidden intent. But even if every line of evidence points to a natural origin, the human urge to interpret, to narrate, and to mythologize remains powerful. Each interstellar visitor becomes both a scientific object and a cultural symbol. reflecting our hopes, fears, and philosophies. Looking back at comets within our own system adds another dimension. We've watched sun grazers disintegrate in solar heat, tails disconnect during storms, and comets brighten unexpectedly before fading to nothing. These precedents remind us that comets are fragile. Oumuamua may have been too depleted to show a coma. Borisov may have been strong enough to endure. Atlas, with its strange chemistry, may reveal yet another fate. The diversity among local comets already spans a wide range. Adding interstellar origins only multiplies the possibilities. There's an educational lesson here as well. Science thrives on comparison. One object alone might be misleading, but three, each different, begin to outline a spectrum. The more we see, the clearer the patterns become. By comparing Oumuamua, Borisov, and Atlas, we begin to grasp the richness of planetary formation beyond our sun. We see that no single system defines the galaxy. Instead, each star may contribute its own style of comet, shaped by its chemistry, its history, and its environment. Taken together, these visitors are like postcards from distant neighborhoods, each carrying a unique picture of home. Personally, I find comfort in this diversity. It tells me that the galaxy is not uniform, not monotonous. It is full of surprises, and that means discovery will never end. Even if we map every local asteroid, every Kuiper Belt object, there will always be more coming from the dark between stars. Each will bring a new question. Some will behave as expected, others will break the rules, but all will expand our sense of what is possible. As we prepare to follow Atlas through its perilous belt crossing and solar encounter, the lessons of past visitors remain in mind. Be ready to observe quickly, be open to the unexpected, and remember that even strangeness is data. In the end, the galaxy is not obliged to fit our categories. We are the ones who must adapt. What lies ahead for Atlas is uncertain. It may survive, it may fragment, it may teach us something so new that textbooks will need rewriting. Whatever happens, its place in the sequence after Oumuamua and Borisov ensures it will not be seen in isolation. It will be part of a story, a trilogy that is just beginning, a trilogy that says, the stars are speaking, one visitor at a time, and we are learning, slowly but surely, how to listen. When most people imagine the motion of planets and comets, they picture neat ellipses, all moving in roughly the same direction around the sun like cars circulating a racetrack. That picture is not wrong, but it hides an important truth. Orbital mechanics allows for far stranger geometries, and Atlas, with its near retrograde trajectory, is among the strangest visitors we have ever tracked. Retrograde means it is moving almost opposite the flow of everything else. Imagine a lone car driving the wrong way down a busy interstate, not weaving intentionally, but bound by a road that was laid down billions of years before. That is what Atlas is doing, cutting through the plane of the solar system at nearly 175 degrees to the direction of planetary traffic. The result is relative velocities far higher than normal. When two objects move in roughly the same direction, collisions are rare and relatively gentle. But when one comes in head-on, the energy of any encounter multiplies dramatically. For Atlas, that means even small encounters with dust or pebbles carry the punch of artillery shells. Astronomers traced its trajectory back and found it was inbound from the direction of Sagittarius, a crowded region toward the galactic center. From there, it fell into our solar system's gravitational sphere, drawn into a hyperbolic path that no planet could capture. Its speed relative to the sun, the so-called hyperbolic excess velocity, was about 58 kilometers per second before gravity added more. By the time it sweeps near Perihelion on October the 29th, 2025, its speed will exceed 65 kilometers per second, a velocity few human-made spacecraft will ever match. The geometry of its approach is as dramatic as the numbers suggest. On October 3rd, 2025, Atlas will skim past Mars at a distance of about 28 million kilometers. That is close enough that spacecraft orbiting Mars-like MAVEN, Mars Reconnaissance Orbiter, and even rovers on the surface may catch sight of the comet. For once, humans have machines in place to witness an interstellar visitor, not only from Earth, but from another planet. It is as though fortune has arranged for multiple vantage points in a cosmic play. From there, Atlas continues inward. In early November, it will pass 0.65 astronomical units from Venus, again, close in astronomical terms, but still safely distant. By March 2026, long after Perihelion, it will pass 0.36 astronomical units from Jupiter. These planetary flybys will not capture it. The energy is too great, but they offer subtle opportunities, tiny gravitational nudges that may shift its exit path by measurable amounts. Astronomers will be watching carefully, since any deviation between predicted and observed positions can reveal additional non-gravitational forces, jets of gas pushing, or even plasma interactions altering motion in ways we do not fully understand. For Earth, the geometry is one of safety and frustration. At its closest in December 2025, Atlas will still be 1.8 astronomical units away, about 270 million kilometers. Safe, yes, but frustrating because Earth will be on the opposite side of the Sun during perihelion, hidden during the most dramatic phase. Only in December, once it emerges from behind the Sun, will telescopes have another chance. By then, whether it survives or fragments, much will already have been decided. Tracking such a trajectory is a feat of coordination. Ground-based telescopes must follow it against dense star fields, compensating for its rapid change of position. Space telescopes like Hubble and JWST must schedule limited time windows, aiming with exquisite precision at a target racing across the sky. Amateur observers provide essential continuity, filling gaps when professional facilities cannot. The entire global community, in a sense, becomes one giant observatory, piecing together a three-dimensional record from countless small contributions. What fascinates me most is how orbital mechanics turns into a story. Each planetary encounter is like a character stepping briefly onto the stage, influencing the plot, then exiting. Mars offers a unique camera angle. Venus provides another gravitational nudge. Jupiter, with its massive presence, bends the outgoing path slightly. Earth, the silent spectator, waits from afar. Atlas itself is the protagonist, moving through a script written not by destiny, but by mathematics. The equations of motion become dialogue, distances become plot twists, velocities become moments of tension. For the public, these encounters also matter symbolically. Mars, long a focus of human dreams, will watch this visitor from close range. Venus, mysterious under its cloud veil, will share a moment too. Even Jupiter, the giant protector of the solar system, will eventually take its turn. Each encounter reminds us that the solar system is not static. It is dynamic, full of crossings and near misses, and sometimes, very rarely, it welcomes travelers from beyond. The retrograde path also maximizes its interaction with solar wind structures. The ecliptic plane, where most planets reside, is also where magnetic sector boundaries, correlating interaction regions, and solar wind turbulence are most intense. Atlas is threading itself directly through this electromagnetic gauntlet, and its plasma tail will serve as a windsock, revealing every invisible gust. By comparing changes in its tail with measurements from spacecraft like Parker Solar Probe and Solar Orbiter, scientists can reconstruct a three-dimensional picture of solar weather. Atlas thus becomes both participant and probe, both victim and instrument. From a personal perspective, I find something poetic in the way Atlas moves against the current. Retrograde motion, to me, feels like defiance. Everything else spins one way, and here comes a wanderer refusing to conform. Yet that refusal is not chosen. It is inherited from the ancient physics of ejection and gravity. Perhaps there is a lesson here about difference. Sometimes, to be different is simply to be. Atlas is not resisting, not rebelling. It is simply following its path. And yet in doing so, it reveals dynamics that conformity would never show. The fact that it travels backward gives us insights we could never have gained otherwise. As it cuts through the belt and approaches the sun, every kilometer marks a new stage in this trajectory drama. Predictions grow uncertain because non-gravitational forces are difficult to model. Outgassing can push it slightly sideways. Jets can alter their spin. If fragmentation begins, the center of mass shifts. Astronomers will watch for these deviations, not only to refine orbital elements, but also to learn about the physics at play. In a sense, Atlas's trajectory is a constantly updated experiment, testing our equations against nature's improvisation. The educational value here is immense. Teachers explaining orbital mechanics to students can point to Atlas as a real-world example: hyperbolic orbit, retrograde inclination, planetary flybys, and perihelion distance. Concepts that might otherwise feel abstract become vivid when tied to a living event. And beyond the numbers lies the deeper point. The solar system is not isolated. Trajectories like Atlas's remind us that the sun is just one node in a web of galactic motion, where objects cross boundaries constantly, indifferent to our categories. As we leave this section, one image stays with me: a small object, perhaps no larger than a city, hurtling at impossible speeds, threading through planetary orbits with the precision of clockwork. Each encounter is scripted by gravity, each deviation written by jets of gas. And we, with our telescopes and equations, watch breathlessly, aware that for all our calculations, uncertainty remains. The future of Atlas, whether it survives, fragments, or transforms, will depend on factors we can measure only imperfectly. The trajectory carries it inevitably forward, toward perihelion and the crucible of solar heating. But before that, speculation about collisions, both dramatic and subtle, will dominate discussion. The myths of Hollywood-style asteroid impacts meet the realities of hidden dust and fragile surfaces. To understand the risks, we must explore collision scenarios, not for Earth's safety, but for Atlas's survival. And that is where the story now turns. Whenever the public hears that a comet is heading through the asteroid belt, one question leaps almost instinctively to mind: will it collide? Hollywood has taught us to imagine cataclysmic impacts, towering explosions, planets threatened, heroic missions to avert disaster. But the real risks, while less cinematic, are no less fascinating. In truth, Atlas is not a threat to Earth or any other planet. Its orbit is known with precision, and there is no possibility of it striking us. Yet the environment it travels through is dangerous to the comet itself. The myths of giant collisions mask subtler, hidden dangers that could determine whether Atlas survives its passage or disintegrates before reaching perihelion. The asteroid belt, for all its reputation, is mostly space. If you were to stand on one asteroid and look around, you would not see a crowded sky of rocks colliding in every direction. You might see nothing at all. The typical distance between kilometer-sized asteroids is millions of kilometers. In that sense, the chance of Atlas hitting a large object is astronomically small. Even in simulations that track thousands of potential paths, the probability of a direct collision is near zero. This is why planetary scientists reassure us that the belt is no minefield. Yet that does not mean Atlas is safe. The true hazard comes from the smallest things, the grains of dust and pebble-sized fragments that float unseen. At the comet's relative velocity, even a grain weighing a fraction of a gram can release enough energy to crack its surface. Multiply that by thousands of impacts over weeks of travel, and the cumulative effect could be significant. Micrometeoroid bombardment is like sandblasting on a cosmic scale. Over time, it erodes, weakens, and can even destabilize the structural integrity of a nucleus already fragile from billions of years of exposure. We know this because we have seen comets fall apart before. Comet Shoemaker-Levy 9 was torn into pieces by Jupiter's gravity before slamming into the planet in 1994. Comet C 2019 Y4, Atlas, fragmented unexpectedly as it approached the Sun. breaking into dozens of pieces visible through telescopes. Comet Ison in 2013 disintegrated during its perihelion passage, leaving only a ghostly trace behind. In each case, no dramatic collision with a large asteroid was required. Stress, heat, and countless tiny impacts were enough. If such events happen to local comets, why not to an interstellar one? For Atlas, the risk is compounded by its retrograde motion. Collisions with dust are not gentle sideswipes, but head-on blows at closing speeds of over 100 kilometers per second. At those speeds, the physics shifts. Materials vaporize instantly, shockwaves propagate through the surface, and fractures can grow. A nucleus that has traveled intact for billions of years can suddenly reveal its vulnerability. Scientists watching from Earth will search for signs of this: sudden brightening, asymmetric jets, or fragments trailing behind. Each of these would indicate that Atlas has suffered a wound in its journey. Hidden risks also come from within. Comets are not solid rocks, but fragile aggregates, porous structures of ice and dust, loosely bound. As sunlight penetrates deeper, gas builds up inside pockets. If the crust is weak or already stressed by collisions, these internal pressures can burst outward. Outbursts of gas and dust may temporarily brighten the comet, but also weaken it structurally. Over time, repeated outbursts can split the nucleus into separate pieces. Thus, even if the belt does not deliver a fatal blow, Atlas's own chemistry may. The educational lesson here is subtlety. Catastrophes in space often do not arrive as singular dramatic events. They arrive as cumulative processes: erosion, heating, internal stress. In daily life, we often imagine crises as sudden explosions, but more often, they come from small, repeated strains. A bridge collapses not because of one heavy truck, but because of decades of tiny stresses. A comet disintegrates not because of one asteroid, but because of billions of grains of dust. To me, this is a reminder that survival is less about avoiding singular threats and more about withstanding the wear of countless minor ones. There is also a statistical element. We know that most comets survive their passages through the belt simply because so many have done so, but the fragile ones are removed silently, leaving survivors as the majority we observe. That means we cannot assume Atlas is safe simply because most are. It may belong to the minority, and that possibility keeps astronomers watching closely. Every flicker in brightness, every odd shift in trajectory is scrutinized as a potential sign of stress. Personally, I find the myth versus reality contrast compelling. It is easy to imagine a fiery collision, harder to imagine the slow disintegration of a fragile body battered by dust. Yet the latter is far more likely, and in some ways, more poignant. To think of Atlas, ancient and immense in its journey, undone not by a grand event, but by countless invisible grains, it is humbling. It reminds me that endurance, whether for comets or for people, often comes down to how we handle the smallest challenges repeated endlessly, not how we face a single dramatic crisis. Observationally, scientists will watch for fragmentation. If Atlas splits, we may see multiple nuclei, each trailing its own small tail. The brightness curve may fluctuate unpredictably. Radio telescopes may detect changes in polarization as dust properties shift. Even spacecraft positioned near Mars or elsewhere in the inner solar system could provide data, giving us a multi-angle view of the process. Each piece of evidence builds toward understanding not only Atlas's fate, but also the resilience of cometary bodies more generally. There is, however, a hopeful side. Erosion and outbursts, though destructive, can also be revelatory. By exposing fresh layers beneath the surface, they allow us to sample material that has not been altered by billions of years of radiation. Spectra of newly released gas can tell us about isotopic ratios, about organic molecules, about chemistry untouched since its birth around another star. In this sense, fragmentation is not failure, but opportunity. Just as paleontologists learn from fossils cracked open by natural processes, astronomers learn from comets broken open by cosmic stresses. So while we worry about Atlas's survival, we also recognize the value of its potential destruction. Whether it sails through intact or crumbles into a family of fragments, it will teach us something we could not learn otherwise. That is why scientists refrain from rooting for one outcome or another. The comet is not a contestant in a game of endurance. It is a teacher, and every fate is a lesson. As Atlas moves beyond the asteroid belt, the spotlight will shift. The questions will no longer be about collisions with rocks and dust, but about the invisible storms of plasma and magnetic fields that surround the sun. These forces too carry risks. They shape the comet's tail, disrupt its structure, and test our models of physics at their extremes. If collisions were the myth, plasma is the mystery, and it is to that mystery that we turn next. When people think of comets, they often picture icy wanderers trailing long, ghostly tails. But for scientists, comets are also laboratories' natural experiments carried out under extreme conditions no machine on Earth could replicate. With Atlas, this role has been magnified 100-fold. As it races closer to the sun, the plasma environment around it transforms from a curiosity into a crucible. Charged particles, magnetic fields, and alien chemistry intertwine in ways that test not just the comet's survival, but the very frameworks of physics we rely on to describe the universe. Plasma is often called the fourth state of matter, distinct from solids, liquids, and gases. It is what happens when gases energize so strongly that its atoms split into free electrons and ions. On Earth, we see plasma in lightning bolts, in neon signs glowing on city streets, and in the hot interiors of nuclear fusion experiments. In space, however, plasma is everywhere. The solar wind itself is a vast ocean of plasma, streaming outward from the sun in all directions. Comets like Atlas do not merely passively endure this stream, they interact with it, creating ripples and storms that echo through space. Atlas is unusual because of its chemistry. Most comets we know are dominated by water ice, with dust and other volatiles mixed in. When water sublimates, it produces H2O plus ions that spiral in magnetic fields in predictable ways. But Atlas is dominated by carbon dioxide. This means that its ion tail is filled with CO2 plus rather than H2O plus, changing the plasma dynamics dramatically. The gyro radius, the circular path charged particles follow in a magnetic field, differs between these species. As a result, the comet's ion tail may develop structures we have never observed before, spirals, kinks, or waves that form naturally as carbon dioxide ions dance in the sun's magnetic field. For me, this is where the story of Atlas becomes philosophical. Imagine a classroom where the teacher sets up an experiment with conditions never tried before. The outcome isn't predictable because the rules are being stretched. Atlas is running that experiment for us on a cosmic scale. The chalkboard is millions of kilometers wide. The equations are written in glowing plasma filaments, and our telescopes are the students scrambling to take notes. One of the most dramatic plasma events comets experience is called tail disconnection. When the solar wind's magnetic field changes abruptly, say, during a coronal mass ejection, the ion tail can be ripped away as if pulled by invisible hands. Time-lapse images show the tail writhing, twisting, and then severing, with the disconnected portion drifting downstream, while a new tail quickly reforms. It is as if the comet sheds one cloak and instantly dons another. For a water-rich comet, this is already dramatic. For Atlas, with its CO2-rich ions, the event could be spectacular, producing filaments and instabilities no one has ever recorded. Laboratory studies of dusty plasmas hint at what might unfold. When tiny charged dust grains are suspended in plasma, they can interact through long-range electric fields, organizing themselves into waves, clusters, and even crystal-like structures. On scales of micrometers in a lab chamber, these effects are mesmerizing. Around a comet, they scale up to kilometers and beyond. Imagine entire regions of space where dust grains arrange themselves into temporary lattices, shifting and collapsing as new ions stream past. These are not just visual spectacles. They are windows into how matter organizes itself under the combined influence of gravity, electromagnetism, and radiation. From a practical standpoint, Atlas offers something researchers dream of: multiple spacecraft positioned throughout the inner solar system, ready to capture different perspectives. NASA's Parker Solar Probe, orbiting closer to the Sun than any craft in history, measures the solar wind's properties upstream of Atlas. The Solar Dynamics Observatory and SOHO observe the Sun's activity, mapping out the storms that will soon slam into the comet. Meanwhile, Mars orbiters like MAVEN can detect changes in plasma downstream when Atlas passes near the red planet. By combining these vantage points, scientists can construct three-dimensional maps of plasma interactions, something impossible with a single spacecraft. Personally, I find this orchestration astonishing. It is as if the universe has set up an experiment, and humanity, by coincidence and persistence, has placed instruments in all the right places to watch. When we send probes like Parker Solar Probe or Mars Reconnaissance Orbiter, we do not know in advance that an interstellar comet will pass by. Yet here it is, threading the solar system at the precise moment when our technology is ready. That alignment is not mystical, but it feels meaningful. It suggests that progress in science is not just about planning, but also about being present and prepared when rare opportunities arrive. The plasma interactions are not just visually and scientifically dramatic, they also matter for the comet's survival. Electromagnetic forces can stabilize or destabilize the nucleus. On one hand, magnetic fields and ion flows might help redistribute stresses, smoothing out the explosive release of gases. On the other hand, sudden reconnection events and electrostatic charging can create pressure points that fracture the crust. Which side wins is an open question, one that only observation can answer. This is an important lesson for us as humans as well. Forces that surround us can either stabilize or destabilize, depending on context. Pressure, whether social, psychological, or cosmic, can sometimes hold us together, giving us resilience. Other times, it splits us apart. Understanding the difference requires not just theory, but lived experience, our own equivalent of telescopes watching the outcome. Atlas reminds us that survival is always a negotiation with the environment. Educationally, studying plasma around comets has broader implications. The same physics governs the auroras that dance over Earth's poles, the radiation belts that protect our planet, and the storms that can disrupt power grids and satellites. It also applies to distant realms, stellar atmospheres, galactic jets, even the interstellar medium itself. Atlas is not just teaching us about itself, it is teaching us about plasma everywhere, from the microcosm to the cosmos. If Atlas fragments, the plasma laboratory will become even richer. Each fragment would develop its own coma and tail, interacting with solar wind in slightly different ways. Suddenly, we would have not one experiment but many running in parallel. Spectrographs could compare how each fragment ionizes, how dust distributions shift, how tails bend and twist. It would be like taking one test subject and splitting it into a dozen, each providing a new line of evidence. As tragic as fragmentation may seem, scientifically, it multiplies the lessons. There is a haunting beauty in this. A comet tearing itself apart is not just destruction, it is revelation. Like a book falling open, each page scattered, but each carrying words we could never read when it was shut. That, to me, is the essence of Atlas as a plasma laboratory. It is less about whether the comet survives and more about what it reveals in the process of survival or disintegration. As Atlas continues its inward plunge, the plasma factor grows central. It is no longer a side note in the comet's story. It is the main arena where forces determine its fate. The tail, the coma, the very glow we see from Earth all are products of plasma interactions. The comet is no longer just a frozen relic from another star. It is a stage on which the universe plays out experiments in electricity and magnetism, with scales and energies we can scarcely imagine. In the next chapter, we turn from plasma to dust, another subtle yet profound hazard. While plasma shapes the comet's external display, dust grains in the asteroid belt threaten to chip away at its very body. And just as plasma interactions hold scientific riches, so too do those tiny collisions. Together, they weave the story of survival and loss, of exposure and revelation, as Atlas sprints toward the Sun. Between Mars and Jupiter stretches the asteroid belt, a region that at first glance seems empty, but in truth is anything but. To the naked eye, it is void. Through the lens of science, however, it is revealed as a bustling environment filled with fragments, some the size of mountains, others no larger than grains of sand. Atlas, racing along its steep retrograde path, must cross this region, and while the dramatic image of a head-on collision with a large asteroid often captures public imagination, the more insidious danger comes from the small things: dust grains, pebble-sized fragments, invisible projectiles that strike at tens of kilometers per second, turning every encounter into a miniature explosion. When a tiny dust grain collides with a comet nucleus at these speeds, the energy released is enormous relative to its size. Each particle acts like a bullet, delivering a shock that can chip away at surface layers. This process, called space weathering, is one of the most persistent sculptors of cosmic bodies. Over billions of years, it has darkened the surfaces of moons, etched craters into asteroids, and altered the spectral fingerprints that astronomers rely on to identify composition. For Atlas, the stakes are even higher. Its nucleus carries unaltered material from another star system, chemistry that has survived the harsh gauntlet of interstellar travel. Every dust grain it meets in the asteroid belt risks destroying or reshaping that record before we can read it. Yet there is irony here. The very collisions that erode Atlas's surface might also reveal its secrets. Just as an archaeologist chips away at encrusted layers to uncover fresher relics beneath, space dust can peel away radiation-hardened crusts, exposing volatile, rich pockets to sunlight. These exposed patches can sublimate rapidly, producing sudden jets that brighten the comet and make it easier for telescopes to analyze. Some of the surprising flares astronomers have already recorded may well be the fingerprints of such micro-collisions. Thermal stress compounds the risk. As Atlas plunges closer to the Sun, its outer layers heat quickly while its core remains frigid, having endured eons in the cold void. This temperature gradient generates internal stress, like hot glass plunged into cold water. Cracks form, volatile gases trapped in fissures seek release. When combined with the constant peppering of dust grains, the result can be unpredictable, sometimes a spectacular outburst, sometimes the beginning of structural failure. History offers cautionary tales. In 2020, comet C/2019 Y4, also nicknamed Atlas, began brightening dramatically, raising hopes for a celestial spectacle. Instead, it fragmented into dozens of faint shards. No asteroid struck it. No tidal force tore it apart. Rather, the accumulated stresses of heat and internal pressure did the work. Similarly, Comet Y, SON, in 2013 inspired excitement as it approached the Sun. But at Perihelion, the solar furnace overwhelmed its fragile body. Within hours, what had promised to be a bright comet became nothing more than a dispersing cloud of dust. The question for 3I Atlas is which path it will follow. Its chemistry is unusual. With carbon dioxide dominating, scientists speculate about its resilience. Some argue that the CO2-rich crust may be tougher, hardened by radiation during its billion-year journey. Others suggest the opposite, that such chemistry makes it fragile, quick to crumble under stress. Neither answer is reassuring, because both are supported by precedents from within our solar system. As Atlas brightens, astronomers watch closely for warning signs. Irregular surges in brightness, asymmetric jets, and sudden changes in coma density all hint at internal strain. Instruments like the Hubble Space Telescope and ground-based observatories using adaptive optics scan for subtle elongations of the nucleus signs that it may be stretching toward fragmentation. Each observation is a kind of health check, a way of asking whether the patient will endure or succumb. But even if Atlas survives the internal stresses, the asteroid belt continues to deliver external challenges. Its coma, now expanding rapidly, acts like a vast net. Dust grains that might have sailed harmlessly past are instead intercepted. Each impact not only strips material, but can trigger chemical fireworks. Unlike water ice, carbon dioxide sublimates at lower temperatures. When dust grains slam into CO2-rich layers, the result can be localized heating that ignites sudden outgassing. Imagine a hammer striking a brittle crust, releasing pent-up vapor that explodes outward, carving jets into the coma. These events may already explain some of the asymmetric plumes we've seen from Atlas's surface. There is also the broader environment to consider. The asteroid belt is not uniform. Dust density varies depending on location and history. Bands of particles, left behind by ancient asteroid collisions, spiral slowly inward under the pull of solar radiation. These dust bands, combined with the zodiacal cloud that fills the inner solar system, create invisible currents of debris. As Atlas crosses these regions, its brightness and tail structure may fluctuate in ways that reflect not only its own chemistry, but the unseen environment around it. In this way, Atlas doubles as a probe of the belt itself, mapping regions of dust density that no spacecraft has charted in detail. For scientists, even destructive impacts hold value. A fragment chipped from Atlas's surface disperses into the coma, where spectrographs can analyze it remotely. A dust grain that bores into its crust may release gases otherwise sealed away. Each micro-collision is an experiment, each jet a revelation. It is as though the asteroid belt itself were assisting us, drilling into the comet to deliver fresh samples to our instruments. Timing, however, is critical. Each week, Atlas remains intact, adds to the scientific harvest. More instruments can lock onto it, more data can be gathered, and more cross-comparisons can be made. Yet each week also deepens its immersion into the densest parts of the belt, increasing the chance of larger impacts. A pebble-sized fragment, invisible to most surveys, could strike with the force of a hand grenade, enough to trigger cascading fractures. The longer Atlas survives, the more we learn, but the greater the risk that survival ends abruptly. Philosophically, I see in this a metaphor for human life and effort. We too cross belts of risk, seasons where every step carries danger. Small impacts. The stresses of daily living can erode us slowly, but sometimes they also reveal hidden strengths, new resources, deeper layers of resilience. The lesson of Atlas is that survival is not guaranteed, but that meaning often comes through exposure, through the balance of vulnerability and revelation. Education thrives on these analogies. Just as Atlas teaches us about dust dynamics, it also illuminates broader processes in the universe. Space weathering is not unique to comets. It shapes airless moons, alters asteroid surfaces, and even influences the soil of Mars. Understanding how micro-collisions work helps refine our interpretation of spectral data, ensuring we don't mistake weathered surfaces for pristine ones. In this sense, Atlas is not only a subject of study, but a calibration tool, helping us decode the entire solar system. In the end, the hidden dangers of dust and mini-collisions may prove as decisive as any catastrophic impact. They will not announce themselves with cinematic drama. There will be no sudden flash visible across the skies of Earth. Instead, the work is slow, relentless, cumulative. A chip here, a crack there, a sudden outburst triggered by an unseen grain. By the time the outcome becomes clear, the process will already have been underway for weeks or months. As Atlas continues, every brightness curve we record may be the last from an intact interstellar nucleus. Every tail structure may be the comet's farewell gesture before fragmentation. This knowledge sharpens the urgency of observation and deepens the poignancy of its story. The dust may not destroy Atlas all at once, but it will test it in ways no interstellar visitor has faced before. And so we wait, watching carefully as the ancient wanderer plunges deeper into the belt. Ahead lies another set of questions. One's less about dust and more about intent. Could such an object, arriving on such a trajectory, be more than natural? Could it be controlled or even constructed? That speculation, controversial and provocative, became a global talking point in mid-2025. It is there, at the edge of science and imagination, that we now turn. In July 2025, only a few weeks after Atlas had been identified as an interstellar visitor, a paper appeared on the Archive that unsettled the quiet rhythm of astronomy. Written by Abraham Loeb and a small group of collaborators, it was labelled carefully as a pedagogical thought experiment, not a claim of discovery. The suggestion, however, was too striking to be ignored. What if Atlas were not a natural comet at all, but something constructed? What if its path, its timing, even its chemistry, pointed not to the slow accidents of astrophysics, but to the deliberate hand of intelligence? The authors hedged their words. They stressed that this was not a declaration, but an exercise, an invitation to imagine how one might evaluate extraordinary claims. Yet the nuance of caution was quickly stripped away once the media took hold of the idea. Headlines across the internet and television screens condensed pages of careful speculation into a single sensational line. Harvard scientist suggests alien spacecraft. The story spread with the speed of wildfire, stoked by algorithms designed to reward engagement, not accuracy. For the public, already primed by earlier debates over the enigmatic Oumuamua, the thought of another messenger from beyond, and this time one spectacularly active, was irresistible. Scientists at NASA and ESA responded with a kind of steady firmness. Their stance remained unchanged. Atlas was, until proven otherwise, a comet, albeit one with peculiar properties. Data from the James Webb Space Telescope showed emission lines of carbon dioxide and water vapor that fit comfortably within the physics of sublimation. Ground-based telescopes watched jets erupting from its nucleus and a plasma tail stretching behind, behaviors entirely consistent with natural outgassing rather than artificial propulsion. Radio telescopes scanned broad swaths of frequency space and found nothing beyond the hiss of thermal radiation and the turbulence of plasma. Even the light curve, which tracks changes in brightness as the nucleus rotates, showed irregularities best explained by a rough, tumbling body rather than a polished construct. Still, the suspicion lingered, and perhaps it was inevitable that it would. The timing of Atlas's arrival was uncanny. It swept into the solar system at precisely the moment when humanity had its most powerful instruments poised and ready, when spacecraft orbited Mars and telescopes in space could coordinate with ground-based giants. Its trajectory was equally provocative. Retrograde, steep against the planetary plane, threading through regions of the solar system, rich with plasma activity and dense with debris. And its chemistry, dominated by carbon dioxide, was unlike anything seen among our local comets. To many outside the scientific community, these coincidences stacked too neatly. It felt like intention hiding in the numbers, as though nature were less likely than design. I understand the pull of that narrative. Humans are creatures wired to see purpose. We glance at clouds and imagine faces. We find animals in constellations of stars. And when a comet carves an improbable path across the heavens, our instinct is to ask not what it is, but why it came. That impulse is ancient and deeply human, but it is precisely what science disciplines itself to resist. The absence of evidence for control, propulsion, or communication weighs more heavily than our sense of coincidence. The simplest explanation that Atlas is natural, though unusual, remains far stronger than the baroque possibility of a perfectly concealed artifact. SETI researchers used the moment to remind the public of what true evidence would look like if an object were artificial. They spoke of narrowband radio signals that carry mathematical patterns rather than random noise. They described how non-gravitational accelerations that cannot be reconciled with sublimation would raise alarms. They pointed out that a truly constructed body would betray itself in the regularity of its light curve, or in isotopic ratios that did not match any known process of stellar nucleosynthesis. And they noted that if Atlas were deploying probes or shedding structures deliberately, high-resolution imaging would reveal geometric arrangements rather than the chaotic sprays of dust we observe in comets. None of these signatures were present. Silence itself became a kind of answer. But the absence of evidence does not silence imagination. If anything, it fuels it. Culture plays a large role here. For more than a century, fiction has trained us to anticipate encounters with alien technology. Arthur C. Clarke's Rendezvous with Rama described a vast interstellar cylinder entering our system. Carl Sagan's Contact dreamed of messages written in cosmic code. Countless films and novels have turned the heavens into a stage for first contact. In that cultural climate, every anomaly invites the question, could this be it? Atlas was a perfect canvas for projection, and the public painted freely. The controversy also illuminated a challenge scientists now face in the age of instant communication. A paper written as an intellectual exercise can become, within days, the foundation of a global rumor. Careful hedging phrases like possibly, hypothetically, or not excluded rarely survive translation into headlines. Speculation becomes assertion, uncertainty becomes drama. The result is both a risk and an opportunity. On one hand, misinformation can take root quickly. On the other hand, interest in cosmic visitors deepens, and the public, however misinformed at first, is drawn toward the frontier of science. My own feeling is that the alien hypothesis has value even if it is wrong, because it sharpens the questions we ask. It forces us to be explicit about what would count as evidence, and it reminds us how to separate anomalies from miracles. It also exposes our biases. With only 3 confirmed interstellar visitors, Oumuamua, Borisov, and now Atlas, we are working with a dataset so tiny that every new case will feel uncanny. The odds that each one will fit neatly into our expectations are small. What we call coincidences may simply be the natural diversity of a galactic population we have barely begun to sample. If Rubin Observatory begins detecting dozens each year, today's mysteries will look ordinary, the way the first exoplanet once seemed miraculous until thousands more were catalogued. There is another dimension, one more personal. Watching the debate unfold, I see a reflection of our yearning. We want the universe to notice us. We want to believe that we are not alone, that some intelligence greater than ours might send emissaries across the dark. And yet the more I sit with Atlas, the more I feel the opposite lesson emerging. Its strangeness does not require intention. Its beauty does not require artifice. It is wondrous precisely. It is natural because it demonstrates that the processes of other stars can create worlds so unlike our own. To reduce that to machinery would be to underestimate nature's imagination. In classrooms, Atlas has already become a case study. Teachers walk students through the scientific method, showing how hypotheses must be tested and falsified. They emphasize that even negative results are data, that the absence of expected signals constrains what is possible. They point out that ruling out the exotic is just as vital as confirming it. Atlas has become not just an interstellar object, but a teaching tool, an exercise in how science protects itself from both wishful thinking and sensationalism. As the comet continues its plunge through the asteroid belt, the alien hypothesis remains what it began as, a thought experiment. It has accomplished its role by sparking curiosity, by igniting debate, and by reminding us that the line between science and imagination is sometimes thin. But the evidence points us back, firmly, to the natural. Atlas is extraordinary not because it is controlled, but because it is free. It is a fragment of alien chemistry, a shard of another star's protoplanetary disk, delivered to us not by deliberate navigation, but by the blind mechanics of gravity. Its story is no less grand for that. And yet, even as the speculation fades, another question presses closer. What if Atlas cannot endure the trials ahead? What if its nucleus, stressed by heat, peppered by dust, and racked by plasma, fails and fractures? What if the ancient traveler that has survived billions of years between the stars meets its end here, in the brief light of our sun? That possibility, haunting and beautiful, draws us into the next part of the story. Imagine a comet that has wandered for billions of years. It has crossed the gulfs between stars, endured cosmic rays, and survived gravitational tugs from countless invisible hands. Then, in the span of a few weeks under the glare of a single star, it begins to break apart. That is the haunting possibility scientists consider for Atlas. The process would begin subtly, with slight irregularities in brightness, asymmetric jets of gas, or shifts in the density of the coma. To the casual eye through a telescope, these changes would be nothing more than fluctuations of light. But to experienced comet watchers, they would signal a deeper story, a nucleus under strain, a body whose internal scaffolding was starting to give way. The physics of fragmentation is brutal. As sunlight penetrates deeper into the crust, volatile materials trapped for eons begin to sublimate violently. Pressure builds within fissures already weakened by thermal cycling in interstellar space. Cracks propagate like fractures racing through ice on a thawing pond. Eventually, the stress exceeds the nucleus's strength, and the comet splits. It may not explode in a single instant, but unravel slowly, piece by piece, in a slow-motion collapse played out across weeks. Observers would notice the signs almost immediately. The central condensation, the bright pinpoint that marks sunlight, reflected from the solid core, would elongate. Instead of one sharp center, multiple luminous knots would emerge, each separating gradually as jets of gas nudged them into slightly diverging paths. These fragments, though tiny on cosmic scales, would still be mountains in size. Some would continue to outgas vigorously, developing their own miniature comas and tails. Others, exhausted quickly, would fade into inert rubble. The once singular tail of Atlas would transform into a braided fan of plasma and dust, a visual signature of a body torn apart. Ironically, the spectacle could be breathtaking. A fragmenting comet often brightens as its surface area increases, releasing more gas and dust into sunlight. To an Earth-based observer, Atlas might suddenly flare into naked-eye visibility, spreading across the sky like a ghostly banner. Yet this brilliance would be temporary. As fragments sputtered out, the glow would fade, leaving behind a diffuse cloud stretching along the comet's trajectory. What begins in wonder ends in dispersal. For those hoping Atlas might produce meteor showers on Earth, the answer would be disappointing. Its hyperbolic trajectory ensures that its fragments will never cross our orbit. Unlike periodic comets that deposit debris streams into Earth-crossing paths, interstellar visitors carry their remnants away forever. The shattered pieces of Atlas would continue into the dark, dispersing across interstellar space, never to return. Our only inheritance would be the images and spectra captured in the brief window of disintegration. From a scientific standpoint, fragmentation is a double-edged sword. On one hand, it destroys the pristine layering of materials within the nucleus, erasing clues about how it was built in its parent star's protoplanetary disk. On the other hand, it exposes fresh surfaces, releasing ices and molecules that had been sealed away beneath radiation-processed crusts. For spectrographs, this is a windfall. Gases invisible before might suddenly bloom in the coma, their signatures spread across infrared and ultraviolet bands. Isotopic ratios, often faint, could be measured with greater precision as larger volumes of gas escape. Even the smallest fragments, glittering as they sublimate, would contribute data points to our understanding of alien chemistry. The emotional impact of such an event should not be underestimated. Comets have always embodied impermanence. They appear suddenly, blaze across the sky, and vanish, often never to be seen again. Atlas, as an interstellar visitor, amplifies that symbolism. To imagine a journey lasting longer than the age of complex life on Earth, ending in sudden disintegration, is sobering. It reminds us that survival, even on billion-year scales, is never guaranteed. Beauty is fleeting, even on cosmic terms. And yet, even in destruction, Atlas would not truly disappear. Its fragments, though dispersed, would carry signatures into the outer solar system, where future spacecraft might stumble upon them centuries from now. Each shard would remain a messenger, albeit one scattered into pieces. In this sense, fragmentation is less a death than a transformation, the comet writing its story in new ways across space. For astronomers, the task would shift from tracking a single object to monitoring a swarm. High-resolution instruments like the Hubble Space Telescope or the adaptive optics systems on Earth could resolve individual fragments, documenting their evolution. Patterns of breakup could reveal whether internal stresses or external impacts were responsible. Was the nucleus porous and fragile, crumbling under heat, or was a dust collision the final trigger? Every detail would refine models of cometary physics, models that could be applied to future interstellar wanderers. The historical parallels are instructive. Comet Shoemaker-Levy 9 fragmented under Jupiter's tidal forces in 1992, its pieces eventually slamming into the planet in 1994 in a display of cosmic violence. Comet 73, P/Schwarzmann-Wachmann 3, broke apart repeatedly between 1995 and 2006, producing a train of fragments that puzzled astronomers. More recently, C/2019. For Atlas and Ison, both succumbed to the stress of solar heating, their hopeful promises of brilliance ending in clouds of dust. These precedents remind us that comets are fragile by nature, and that survival near the sun is never certain. Atlas may prove no exception. I find myself dwelling on the symbolism of this possibility. If Atlas breaks apart, we will witness not just the end of an object, but the conclusion of a journey that began when the Milky Way itself was younger. A billion-year traveler dissolving under the gaze of our telescopes is a reminder of the fragility that connects us to something deep. Human lives are brief, measured in decades. Civilizations endure for centuries. Yet even billion-year journeys can end suddenly, undone by forces as ordinary as sunlight and dust. There is humility in that recognition. At the same time, fragmentation would be a kind of gift. The comet's interior, sealed since its birth, would be offered to us in a final act of revelation. Spectrographs would record molecules forged in another star system. Telescopes would capture the dance of fragments as they drift apart. Computers would model the process, teaching us how ice, dust, and carbon dioxide behave under stresses no laboratory can reproduce. What seems like loss is also discovery. The lesson applies beyond astronomy. Breakdowns, whether of comets or of people, often reveal what lies beneath. A body or a life under pressure sometimes splits, but the fragments tell truths that the intact whole concealed. Atlas, if destroyed, would embody that paradox. A tragedy for continuity, but a triumph for knowledge. Ultimately, whether Atlas survives or shatters, it will not leave us empty-handed. If intact, it continues as a living probe of alien chemistry. If destroyed, it multiplies into many probes, each carrying part of its story. The outcome matters less than our readiness to learn from whatever unfolds. As Atlas hurtles towards Perihelion, the possibility of destruction is real, supported by precedent and hinted at by its erratic behavior. Scientists remain vigilant, instruments poised to capture every flicker of light, every plume of gas, every elongation of its core. The comet may survive, defying expectations, or it may fracture, leaving behind only a cloud of dust and data. Either way, the message is clear. Impermanence is the law, but within impermanence lies revelation. From here, the imagination takes another turn. If Atlas does not survive, the question of its fate is answered in finality. But what if it does? And what if, against all odds, its trajectory could be altered, not shattered into fragments, but redirected into a new orbit, captured somehow by the gravity of our system? That fantasy, improbable though it is, has captured imaginations for centuries. It is the scenario we consider next. The thought has a seductive power. What if, after billions of years wandering the void, Atlas was somehow captured by our sun and kept here, a permanent resident of the solar system? The very idea transforms an interstellar visitor into a cosmic neighbor. Instead of racing away into the galactic wilderness, never to return, it would circle among the planets for centuries or millennia, a companion we could visit, study, even dream about colonizing in the distant future. Humanity is wired to imagine adoption stories like this, an orphaned traveler brought into the family of our star. Yet the hard truth of physics is merciless. Atlas is moving too fast. Its hyperbolic excess velocity, what orbital mechanics calls V infinity, is about 58 kilometers per second. That is not just fast, it is uncatchable. To trap an object into a bound orbit around the sun, the system it enters must bleed away almost all of that excess energy. Jupiter, the most massive planet we have, can alter its orbit by a few kilometers per second during a close pass. Mars and Venus can nudge by less. None can erase tens of kilometers per second. To make Atlas bound would require draining more than 99% of its energy, an act of cosmic braking beyond the reach of natural encounters. Still, the fantasy lingers because orbital mechanics is not intuitive. People hear of slingshot maneuvers used by spacecraft Voyager stealing momentum from Jupiter, Cassini borrowing from Venus, and wonder why the same cannot apply here. But slingshots only work in certain configurations. Atlas is retrograde, moving opposite to the planets. That orientation makes gravitational assists weaker, not stronger. Instead of bleeding off speed, most encounters only bend their path slightly, like a river current deflected by rocks, but never slowed. Even the closest planned encounter, a pass by Mars at 0.19 astronomical units on October 3rd, is too distant to provide meaningful capture. The red planet will tug, yes, but only enough to shift Atlas's outbound trajectory by small angles, changing the details of its departure, but not its destiny. Capture requires a dissipative force, something that absorbs energy. In planetary systems, this can be tidal interaction, atmospheric drag, or collisions. But Atlas will never skim close enough to a planet to feel tides, never dip into an atmosphere, never strike another body head-on. It will pass through, untouchable. Without that braking, it cannot be trapped. Yet there are subtler ways trajectories evolve, and they are worth considering. Comets accelerate and decelerate under non-gravitational forces produced by their own jets. When gas vents from the surface, the escaping molecules act like rocket exhaust, imparting thrust to the nucleus. For most comets, these accelerations are tiny, measured in millimeters per second per day. But accumulated over months, they can shift an orbit noticeably. Rosetta's long campaign at Comet 67P showed how asymmetric jets altered its orbital period by minutes each passage. If Atlas develops strong directional outgassing, the effect could be amplified. With its unusual carbon dioxide dominance, the jets may erupt differently from water-based ones, creating thrust profiles unfamiliar to our models. Still, even the strongest plausible non-gravitational forces cannot erase a hyperbolic excess of 58 kilometers per second. They can tilt the exit angle, change the timing of perihelion, or shift the comet's path by fractions of a degree. They cannot transform a visitor into a resident. Atlas will leave, regardless of how much it roars and vents on the way. Its destiny is to depart. And yet, thinking about capture is not wasted. The speculation illuminates important lessons. It shows why orbital mechanics is unforgiving, why energy is the true currency of motion. It also underscores how improbable bound captures of interstellar comets must be. The ones we will someday study long-term will not be those that wander in accidentally, but those we deliberately chase with spacecraft. If we wish to adopt an interstellar visitor, it will be through technology, not celestial coincidence. There is another, more fanciful idea that surfaces in late-night discussions. What if Atlas hides in plain sight? Could it, by chance or design, embed itself among the asteroid belt, masquerading as a local? The answer is equally clear. Hyperbolic orbits never close. They are escape trajectories, not loops. Once perihelion is passed, Atlas will speed away, outbound forever. The belt will not hold it. The planets will not cage it. Its stay is temporary, no matter how deeply we wish otherwise. But subtle redirections do matter scientifically. When Atlas re-emerges from solar conjunction in December 2025, astronomers will scrutinize its trajectory with exquisite precision. Any deviation from predicted paths, tiny changes in velocity, slight shifts in inclination will be catalogued. If non-gravitational forces act strongly, those deviations will reveal much about the pattern of jets and the internal structure of the nucleus. If electromagnetic interactions with the solar wind impart measurable effects, we may glimpse new forces at play in dusty plasma dynamics. Every shift, no matter how small, carries information. Spacecraft throughout the inner solar system provide multiple vantage points for this measurement. Mars orbiters may glimpse Atlas during its October approach. Venus missions might detect its passage weeks later. Even solar probes like Parker can contribute by recording upstream plasma conditions. Each dataset adds to the triangulation, refining models of where the comet will be when it exits. By the time it disappears back into interstellar space, its orbit will be one of the best determined in history. To me, there is beauty in this certainty. The fantasy of capture is emotionally appealing, but the reality of departure is more profound. Atlas is not meant to stay. It is meant to pass through, a messenger from elsewhere whose value lies in its impermanence. To desire otherwise is to misunderstand its role. We do not need to cage it. We need to listen while it is here. There is also relief in inevitability. If Atlas could be captured, it might also pose risks. A captured interstellar body, looping unpredictably among planets, would add complexity to celestial mechanics and hazard assessment. But its outbound trajectory means it poses no threat. Even if it shatters into fragments, each will continue outward, never intersecting Earth. The comet's story is one of observation, not defense. We can study without fear, secure in the knowledge that it will not linger dangerously. I often think of Atlas as a cosmic ambassador. It brings with it the chemical history of another star. Samples of alien ice and dust forged billions of years ago. It stays briefly, then departs, carrying traces of our solar system outward in exchange. When sunlight scatters through its tail, some of those molecules are not ancient, but new hydrogen from our solar wind, electrons from our magnetosphere. In leaving, Atlas carries part of us. The exchange is mutual, even if unconscious. It is less adoption than visitation, less capture than conversation. Educationally, this moment is powerful. Students learning orbital mechanics can trace Atlas's trajectory, calculating why capture is impossible. Those studying plasma physics can model how jets alter paths. Observers in amateur astronomy clubs can track changes in its brightness and position night by night. Even the broader public, drawn in by headlines about alien spacecraft, is offered a lesson. The universe is not arranged for our convenience, and natural law resists our wishes. Atlas is a teacher, whether we grasp the equations or simply watch the glow. From a philosophical view, I find comfort in impermanence. There is temptation to cling, to want Atlas to remain where we can study it forever. But impermanence sharpens attention. It reminds us to act now, to observe, to treasure the brief window we are given. In human life, as in cosmic events, it is often the transient that holds the most meaning. Atlas is meaningful precisely because it cannot be kept. As we imagine the impossible, the comet settling into a new orbit, circling our sun for centuries, we confront what is real. It will not. It will exit, carrying mystery back into the dark. And that is enough. In its passing, it will leave us data, questions, and wonder. That is all a teacher owes a student. That is all a messenger must do. When December comes, and Atlas reappears in the dawn sky before fading into invisibility, we will measure the changes, record the lessons, and say farewell. It will not stay, but it will not be forgotten. Its redirection is not into a permanent orbit, but into our awareness, our science, and our imagination. That is a kind of capture no physics can forbid. And yet, even as we release the fantasy of a bound orbit, another speculation returns, one harder to dismiss, the alien hypothesis. If Atlas is not natural, if its passage is intentional, then the question is not whether it will be captured by gravity, but whether we are already caught in its purpose. That is where the debate takes us next. Speculation has a way of running faster than evidence, especially when the subject is something as rare and mysterious as an interstellar visitor. From the moment Atlas was identified, whispers about its possible artificial nature surfaced. A preprint paper suggested that while natural explanations were overwhelmingly likely, it was not unreasonable to keep technological hypotheses in mind as teaching examples. That nuance was lost almost immediately. Headlines leapt to phrases like alien probe in our solar system and hostile visitor racing toward the sun. In a matter of days, the comet was no longer just a scientific discovery. It was a cultural event, distorted by the machinery of media and imagination. The scientific community responded cautiously but firmly. Natural explanations had to be tested first, and so far, every line of evidence pointed in that direction. The chemical signatures, dominated by carbon dioxide in an 8-to-1 ratio with water vapor, were strange compared to local comets, but still compatible with natural processes in foreign protoplanetary disks. The isotopic ratios that telescopes managed to resolve fit comfortably within the expected ranges of stellar nucleosynthesis. Nothing about the material hinted at manufacturing or refining. The light curve showed irregularities, yes, but those were consistent with a rotating, lumpy nucleus venting gases, not with the polished symmetry of a machine. And yet the public clung to the possibility. Part of it was precedent. In 2017, the elongated body named Oumuamua had baffled astronomers with its odd acceleration and lack of visible coma, leading some to propose that it might be a light sail or fragment of alien engineering. Even though later models explained its behavior with more prosaic physics, the idea stuck. Once the possibility of alien probes entered popular consciousness, each new interstellar visitor would be shadowed by the same suspicion. Social media algorithms deepened the effect. Posts that shouted alien mothership traveled farther and faster than those that said unusual chemistry. Engagement rewarded the extraordinary. Within weeks of Atlas's discovery, forums were filled with speculation about hidden probes, cloaked transmitters, or deliberate trajectories designed to fly past Mars at a distance convenient for observation. The fact that orbital mechanics dictates such paths and that Mars encounters are common on hyperbolic approaches did little to slow the narrative. For scientists, this created a dilemma. To ignore the speculation risked losing the public conversation to exaggeration and conspiracy. To address it directly risked amplifying the very claims they wished to temper. Many chose a middle path, acknowledge the fascination, explain why extraordinary claims require extraordinary evidence, and point to what observations would constitute genuine signs of artificiality. Those included structured radio transmissions, controlled acceleration beyond what jets could explain, geometric regularity in the nucleus, or isotopic anomalies impossible to produce naturally. None had been observed. SETI researchers, however, did not dismiss the moment. They saw it as an opportunity. Even if Atlas was natural, it represented a chance to test their listening infrastructure. Breakthrough, Listen, and other projects scheduled observations at radio frequencies, monitoring during the Mars flyby, and again at Perihelion. The exercise was not wasted. A null result is data. It constrains the possibility space. It shows what signals are absent, In science, silence is itself a form of evidence. The cultural dimension fascinated me as much as the science. Why do people leap so quickly to the alien hypothesis? Part of it is narrative hunger. Humanity has always told stories of messengers from the sky, of omens and visitors. An interstellar comet is a blank canvas on which we paint our oldest myths in modern language. Another part is the deep desire for connection. To imagine that Atlas is artificial is to imagine that we are not alone, that intelligence elsewhere has reached across the void. Even if the object is hostile, the very fact of its existence would end cosmic loneliness. That hope outweighs caution in the collective imagination. From an educational standpoint, the episode reveals the importance of teaching how science deals with uncertainty. Hypotheses are not conclusions. They are stepping stones. A scientist may pose the alien hypothesis not because they believe it, but because testing it sharpens our tools. If the claim is that an object is artificial, then the prediction is clear. It should produce signals. It should maneuver. It should display symmetry. If those predictions fail, the hypothesis falls. That is the method at work. But in public conversation, hypothesis and conclusion blur. The suggestion itself becomes evidence in the eyes of many, even when scientists intend it as a foil. As Atlas crossed the asteroid belt, telescopes reported nothing inconsistent with natural behavior. Its coma expanded, its tail shifted under solar wind, its brightness flickered with outgassing. Each detail added to the case that this was an unusual comet, not a disguised craft. But the speculation would not die. Some insisted that advanced probes could mimic natural chemistry, could release gases deliberately to appear cometary, and could hide within expected ranges. This argument is unfalsifiable. If every natural behavior can be explained as camouflage, the claim can never be disproved. That is why science resists such reasoning. A good hypothesis must risk failure. Still, I find value in the public's fixation. It drives attention to astronomy. It prompts people to learn about eccentricity, perihelion, spectroscopy, and isotopes. Even if they begin with the wrong question, they often end with new knowledge. That is not trivial. It means the alien hypothesis, however overblown, serves as a gateway to genuine curiosity. In classrooms and online discussions, teachers used Atlas to explain why outgassing creates acceleration, why orbital mechanics makes capture impossible, and why carbon dioxide dominance is unusual but not impossible. The alien story brought students to the table. The science kept them there. Personally, I think the truth is even more inspiring than the speculation. Atlas does not need to be artificial to be extraordinary. It is a relic of the thick disk of our galaxy, formed billions of years before our solar system existed. It carries chemistry shaped in stellar nurseries we may never map. Its trajectory threads the asteroid belt in retrograde defiance of local order. It is more alien as a natural object than as a machine. A probe is an echo of ourselves. A comet like Atlas is something genuinely other, unshaped by familiar hands. That perspective is worth repeating. The universe is stranger than fiction. We do not need to invent extraterrestrial engineers to encounter the unknown. Nature has already built wonders beyond our imagination. When people ask me if I think Atlas could be a spacecraft, I tell them this: it doesn't have to be. The truth that we are brushing against chemistry born around another star, preserved for eons, now unraveling under our sun, is more powerful. We are touching timescales and processes that dwarf human industry. We are glimpsing the galaxy's autobiography in ice and dust. Still, the speculation leaves lessons for the future. As the Rubin Observatory begins operation, detecting dozens of interstellar visitors each year, the alien question will return again and again. It will be the responsibility of scientists and communicators to frame discoveries carefully, to distinguish between genuine anomalies and cultural projections. We must be ready for the next wave of headlines, the next viral post declaring probe inbound. We must be ready to teach, to explain, to hold space for imagination while guiding it toward understanding. and we must also acknowledge the ethical dimension. If one day evidence does emerge, radio pulses repeating prime numbers, maneuvers beyond physics, materials unknown to nucleosynthesis, what then? Who speaks for Earth? How do we disclose without panic? How do we balance openness with caution? Atlas may not force those questions, but its speculation provides rehearsal. It is a dress rehearsal, not for proof, but for possibility. In the end, Atlas remains natural. The alien hypothesis has generated fascination, but evidence has not followed. That is science doing its work, proposing, testing, discarding. What remains is not disappointment but awe at what natural processes can achieve. The carbon dioxide coma, the retrograde path, the survival through the asteroid belt. These are marvels in themselves. The extraordinary resides not in machines disguised as comets, but in comets that behave so differently they make us think of machines. As Atlas continues toward Perihelion, its story illustrates a paradox. The alien hypothesis began as speculation about control, but the real control is exercised by physics. The comet is not a vehicle with intent. It is matter responding to energy, ice responding to sunlight, dust responding to plasma. Yet in obeying those laws, it reveals a cosmos vast enough to contain both our longing for contact and the reality of strangeness without agency. It shows us that nature alone can supply mysteries worthy of wonder. And so the question shifts. Instead of asking, is Atlas artificial? Perhaps the deeper inquiry is, why do we need it to be? The answer lies in human desire for connection, for narrative, for meaning. But Atlas, in its silence and its chemistry, tells us another story, that meaning does not require intent, and wonder does not require design. The universe is enough. Atlas is not the end of a story, but the beginning of one. For all its strangeness, it is just the third confirmed interstellar object humanity has encountered, and even its uniqueness must be weighed against the reality of small number statistics. 3 examples are not a trend. They are a hint, a glimpse, a whisper of a far larger population drifting unseen through the galaxy. The wake-up call that Atlas delivers is not only about its own mysteries, but about the flood of discoveries soon to come. Standing on the cusp of a new observational era, we are about to learn that interstellar visitors are not once-in-a-lifetime anomalies, but regular participants in the story of our solar system. The key to that transformation is the Vera C. Rubin Observatory in Chile, scheduled to begin its legacy survey of space and time within the next year. Unlike the piecemeal sky surveys of the past, Rubin is designed to capture the entire southern sky every few nights with unprecedented depth and sensitivity. It will produce a dynamic map of the heavens, not static, but alive, capable of detecting faint, fast-moving objects that slip past traditional telescopes. For interstellar comets, Rubin is the game-changer. Where Pan-STARRS and Atlas could find one visitor every decade, Rubin could reveal one every year, perhaps more. Some estimates suggest a dozen annually once its full cadence is established. This changes everything. The first interstellar visitor, Oumuamua, was a fleeting blur. Detected late, it was already outbound, leaving astronomers scrambling to observe before it faded beyond reach. Borisov, the second, was brighter and better studied, but still left as quickly as he arrived. Atlas has given us months of preparation, yet even here, timing feels tight. With perihelion hidden by the sun's glare and spacecraft missions too slow to intercept, with Rubin, the calculus shifts. Early detection means we can plan, coordinate telescopes globally, and even launch rapid response probes if the right object appears. What once was serendipity becomes strategy. The implications extend beyond astronomy into technology and policy. Space agencies are already discussing mission concepts for the rapid interception of interstellar objects. Small, agile spacecraft equipped with cameras, spectrographs, and dust collectors could be launched on short notice to fly by a newly detected comet within months. The technology exists, but the infrastructure funding, coordination, International agreements remains fragile. Atlas highlights the urgency. If we want to meet these messengers up close, we must be ready before they arrive. Delay means lost opportunity, and in the case of hyperbolic trajectories, opportunity never repeats. For planetary science, the arrival of frequent visitors redefines what cosmic sampling means. For centuries, our understanding of comets was limited to the handful that returned periodically or were bright enough to observe in passing. The Rosetta mission to Comet 67P showed how deeply complex even a single local body could be, with cliffs, plains, dust storms, and jets forming a landscape as alien as any planet. But interstellar comets bring chemistry shaped under different suns, frozen histories of disks far from ours. Each one is a sample of another solar system, delivered freely, without the need for interstellar travel. Rubin will give us a library of such samples, an archive of alien building blocks to compare against our own. The diversity will teach us whether our system is typical or unusual, whether water-rich comets dominate the galaxy, or whether exotic chemistries like Atlas's CO2 dominance are common. For astrobiology, the stakes are profound. If life's precursors are widespread in cometary ices, then panspermia, the seeding of planets by drifting material, becomes more plausible. Each interstellar comet is a test of that idea, carrying molecules forged under unfamiliar conditions, perhaps hinting at biochemical recipes we have not imagined. Even null results are data. If most comets prove barren of complexity, that too tells us something vital about the rarity of life. The Rubin era will not only expand our catalogue of rocks and ices, it will probe the question of whether life is inevitable or exceptional. The cultural impact may be equally transformative. Until recently, humanity thought of comets as omens, then as icy leftovers of planetary formation, then as occasional spectacles in the night sky. Now we know they are also messengers from beyond the sun's family. With dozens detected each decade, public awareness will grow. News cycles will no longer erupt around a single anomalous visitor, but instead follow a drumbeat of arrivals. Each will be given a name, a story, and a chance to fire the imagination. Some will be faint and fleeting, others bright enough to be seen without telescopes. Children will grow up in an age where interstellar comets are not once-in-a-century wonders, but expected events, part of the fabric of the sky. That normalization carries risks. Familiarity may dull excitement, but it also promises a deeper embedding of cosmic perspective in everyday culture. From my point of view, the Rubin era is a test of maturity. Atlas has shown how quickly speculation can spiral into hype, how fragile the line between science and storytelling can be. When dozens of visitors arrive, the temptation to label each one extraordinary will be strong. Alien probe theories will surge with every new detection, amplified by media ecosystems that thrive on sensation. The challenge will be to cultivate a public literacy that can balance imagination with discipline, wonder with skepticism. Scientists must learn to communicate better, faster, and with humility, acknowledging uncertainty without letting speculation outrun evidence. The ethical dimension also grows sharper. With many visitors, the odds increase that one will present genuine anomalies, unexpected acceleration, bizarre chemistry, even signals that defy natural explanation. If such an object is found, the world will demand answers. Who interprets the data? Who decides what is shared when and how? The international scientific community will face unprecedented responsibility. Atlas, in all its drama, has been a rehearsal. Rubin will provide the full performance. Education will flourish in this new landscape. Students will track live discoveries, calculate orbital parameters, and analyze spectra in real time. Amateur astronomers will participate, contributing follow-up observations with backyard telescopes. Citizen science platforms will integrate Rubin's torrent of data, turning the hunt for interstellar objects into a global activity. The very act of searching will democratize discovery, spreading ownership of the sky beyond institutions. I imagine classrooms where children compete to find the next visitor in Rubin's public data streams. their excitement carrying them into futures as scientists or engineers. The age of interstellar comets will be an age of inspiration. But the wake-up call is not just about science. It is about perspective. Each interstellar visitor is a mirror in which we glimpse ourselves. They remind us that we are not isolated, that the solar system is porous, that material constantly flows between stars. We are part of a galactic ecology, threads in a web larger than our sun, our planets, our histories. To acknowledge that is to shift identity from local to cosmic, from citizens of Earth to citizens of the galaxy. That shift will not happen overnight, but each new detection will push it forward, step by step. When I reflect on Atlas, I see both a singular mystery and a symbol of what is to come. Its chemistry, its retrograde path, its possible fragility, all are unique, but uniqueness will fade in the flood of discovery. Soon we will see dozens of stories like this, each with its quirks and lessons. The true significance of Atlas is not that it is extraordinary, but that it is ordinary enough to remind us what awaits. The Rubin Observatory will turn a trickle into a torrent. We stand on the threshold of abundance, and yet abundance does not erase wonder. Each visitor is still a relic of alien origins, a shard of another world drifting through ours. Each carries history older than Earth, silence deeper than language, journeys longer than human imagination. The wake-up call is not just scientific, it is philosophical. We live in a galaxy alive with travelers, and we are only now learning to notice. Our task is to listen, to measure, to imagine, and to understand. As Atlas races toward Perihelion, we know it will leave us soon, but behind it comes a future where such departures are no longer final, because arrivals will follow. The age of rarity is ending, the age of encounter is beginning, and with it comes the realization that what once felt miraculous is in truth the steady heartbeat of the galaxy. In the end, what matters most about 3i Atlas is not whether it fragments or survives, not whether its chemistry rewrites textbooks or simply adds another line of data. What matters is the mirror it holds up to us. For billions of years, it has wandered between stars, unseen, untouched, indifferent. Only now, at this brief intersection with our solar system, does it become visible. And in its fleeting glow we glimpse our own reflection. Atlas reminds us that we are not alone in the cosmos, not in the sense of intelligent neighbors, but in the sense of shared material, shared histories, shared origins. The dust that forms its tail is the same dust that seeded our world. The ices that sublimate from its surface may echo the ices that once rained on Earth to deliver water and organic molecules. To watch it pass is to watch our own beginnings replayed in miniature. But the mirror is not only historical, it is also moral. What will we do with the gift of such encounters? Will we meet them with curiosity, with patience, with humility, or will we project our fears and fantasies onto them, rushing to declare answers where only questions exist? Atlas cannot speak, yet it asks us to listen to the silence of space, to the fragility of worlds, to the long continuity of matter moving through time. As this visitor fades back into interstellar night, others will follow. Each will be a chance to practice seeing more clearly, to recognize ourselves as participants in a galaxy alive with motion. That, perhaps, is the true cosmic mirror, not a reflection of our uniqueness, but of our belonging. If this journey has carried you somewhere meaningful, I invite you to subscribe, to share, to leave your thoughts. In doing so, you help keep the conversation alive, and together we continue learning from the messengers that pass through our skies.